Hi, am I audible? Good morning to all the dignitaries present here today. I'm presenting a paper on stickies and odor control today on behalf of Anmol Polymers, specifically in the recycled paper mills. So the agenda will be simple. We'll just introduce what the problem of stickies is, then we'll talk about how to control them, and then we'll go to the second part of the presentation, which is problem of odor and how to control it. So as you all know, today most of the paper manufacturers are producing paper in a closed loop system, and I want to take a second and appreciate every one of them for doing so to conserve water and energy. However, this achievement has led to its problem of its own. So prime amongst them have been the problem of stickies and odor in paper. So paper manufacturers today have to utilize different types of furnish, and often these furnishes are contaminated with pressure-sensitive materials like hot melt adhesives, tapes, seals, bindings, decals, stamps, etc. So these adhesives and other contaminants, they are collectively responsible for both stickies and odor in paper. So stickies are a diverse mixture of synthetic polymeric organic material which are generally found in the recycled paper making process. Stickies are liberated from the recycled fibers in the pulping process due to mechanical and thermal energy. Much of these are removed in the screening, cleaning, flotation, and deinking processes. However, some of the tacky forming material is there and which forms to build sticky deposits. Such deposits can lead to frequent paper breaks and affects the life of the felts and fabric. It causes downtime due to the frequent wash-ups and boil-outs. So depending on the size, these stickies can be segmented into macro and micro stickies. Micro stickies are basically able to pass a sieve of 0.1 mm, and macro stickies are basically larger stickies which can be easily retained on the screen. But particles smaller than 1 micron remain in the colloidal stage and are called potential stickies. So there's not stickies as of now, but they have the tendency to agglomerate and build up stickies later in the system. In this paper, we try to address the problem of potential stickies. A little about the sources of stickies. So the sources of stickies can be pressure-sensitive adhesives like hot melt adhesives, adhesives like binders, lubricants, gums, starches, waxes like paraffin waxes, latex from coated book stock. Microbial growth also contributes to the problem of stickies. Chemical additives like AKD, starch, DSR, guar gum especially, scale deposits, etc. I'm sure most of you all know what hot melt stickies are, but I'll just go ahead and define it. So hot melt stickies are basically adhesives which are applied in a molten state in order to form a bond upon cooling. So when this paper containing the hot melts is recycled and passes through pulpers and high shear mechanical processes, the hot melts are sheared and broken down into particles, which much of them goes into the colloidal stage. In this slide, we'll talk about the nature of contaminants. First, we'll talk about suspensions, which are basically particles which are larger than 0.1 mm and can be easily removed by screening and cleaning processes. At second, we have microbial growth, which can be tackled with an effective biocontrol program. At third, we have colloids, which are basically particles smaller than 1 micron, but larger than 10 to the power of minus 2 microns. Then we have solubles, which are organic compounds of high molecular size, and the range is somewhere between 10 to the power of minus 2 to 10 to the power of minus 3 microns. At last, we have ionic solutions, which are inorganic compounds in the form of ions, which are less than usually 10 to the power of minus 3 micron. But in a closed water circuit, the ion concentration reaches a precipitation point and contributes to colloidals. Together, they constitute colloidals and potential stickies. A little more about colloids. The colloids have a diverse nature and can constitute of the following. So it can constitute to wood extractive, soluble adhesives, white pitch, ink, hydrolyzed sizing agent, biofilm, scale, etc. However, colloids can be destabilized by chemical coagulation. Not much of it can be removed, so hence we have the problem of stickies. If the balance can be all mopped up, we can have a cleaner system and less chances of sticky formations later in the stage. Unfortunately, there is no direct measurement of colloidal concentration. We have turbidity, but it is a relative measure. That was all about the problem of stickies. Now the question rises how to control them. So we believe that these stickies need to be controlled on a macro level, and it needs to be done with a holistic approach. For that, first of all, we need a good screening and cleaning processes to take out the macro stickies. After that, we need timely boil-outs. We need use of coagulants and flocculants, an effective biocontrol program to tackle the microbial growth, biofilm dispersant to break the colonies of bacteria, wire passivation, and use of scavengers like bentonite. Due to the diverse constitution of the sticky forming colloids, it makes practical sense to use scavengers such as bentonite. Bentonite works on the principle of adsorption, and it is largely independent of the charge. It is a natural clay product derived from various mines. It is activated by a chemical treatment in order to impart specific functionalities. The most important point is it has the property of exfoliation when dispersed in water. The clay opens up into nanoplates which provide a large surface area. To my astonishment, 1 gram of bentonite can spread up to 800 square meters, which is as big as a football field. The large surface area serves to absorb all colloidals and the potential stickies. But not all bentonites are same. For a bentonite to function effectively in paper making, it must be sourced from the right mine. It should be suitably activated and dispersed under high shear before using. So the activation, which is the alkaline activation to introduce sodium ions to replace the Ca ions, is very important. This allows hydration and intercrystalline swelling called exfoliation, which produces the large surface area. Now, even after you have an effective bentonite, it won't work properly till the time it is prepared properly. So the dispersion of bentonite under high shear at the user's end determines that it exfoliates properly. Now we examined different samples of bentonite all over the world to check the fixation of the hydrophobic particles, and we found that the sample from North Africa, which is essentially from Egypt, shows highest fixation of the hydrophobic particles, which is 34% as compared to other areas. Hence, we say all bentonites are not the same. In this slide, you can easily see how on the left corner, there is a bentonite which is air dried, and when hydrated, it swells up. But still, it is like a stack of cards. Until we introduce the sodium ions, swelling does not happen properly. Now you can see here, the swelling is happening over and above the nanoplates, and hence the nanoparticles basically slide over one another to form a dispersed and form a larger area. So this is a good sample of bentonite, which even after 48 hours exhibits good thixotropic behavior, which is it gels while it is stationary, and it becomes liquid when it's shaken. On the other hand, this sample of bentonite displays poor exfoliation, as after 48 hours it is still very watery and shows phase separation. So all bentonites are not same. Now in this diagram, you can easily see that the bentonite is able to absorb almost 65% of the potential stickies, which are sized from 0 to almost 5 microns, as compared to talc, which is only able to mask somewhere around 33% of the micro stickies and macro stickies. And even in the micro stickies, the size is almost above 5 microns. This is because bentonite as a nanoparticle is of similar size and with particles with similarities. These colloids basically fix on the surface and are not able to react with one another to form basically agglomerate or form visible stickies. So even after adsorption of the colloids, the bentonite nanoparticles still remain below 1 micron. So they are immune to the shear forces in the pumps, tanks, and pipes. Hence, they are inert to any destructive forces on its way to the paper machine. Now we come to the second part of our presentation, which is odor problem in paper. Again, because of the most recycled paper mills manufacturing in a closed loop system and using high quantity of starch. Also, the waste paper which is available today itself has a lot of contaminants. This leads to microbial growth, and due to this, the problem of bad odor is rising on a daily basis. With reason that the anaerobic bacterial activity is the main cause for odor. These microorganisms produce volatile fatty acids, which we also call VFAs, and they also produce hydrogen sulfide gas through the activity of sulfate-reducing bacteria. Measure of VFA and SRB, it indicates the presence of the odor-forming compounds, but it does not pinpoint to the exact source. Hence, there is no all-conclusive testing for odor. Only the smell test has proven effective to test odor. We have found that a biocontrol program also helps in reducing odor. So for example, for that, we need a periodic boil out so that the system is clean when we start the biocide program. We need to ensure there is proper aeration in the system and there is no stagnancy of water in the water circuit. Third and most important is using oxidizing and non-oxidizing biocides. After that, we need to monitor the effectivity of the biocide program by measurement tools like ORP and residual oxygen. Then we also need to use bacticides from time to time to check the presence of SRB, TBC, and fungal spores. But we've found that even after an effective bio program, there are some fungal spores which are very persistent and can even survive the heating zone of the paper. They have a tendency to develop fully later. Hence, it is observed that when the paper is leaving the paper mill, it is odor-free. But upon storage or in overseas shipment, and when the shipment is opened at the customer end, there is bad odor problem there. The solution is only to have a slow-release biocide, which can afford a long-term protection. And so we have collaborated with a research-based company to introduce micro-encapsulated biocides. The actives which are encapsulated are a mixture of synthetic and natural biocides to effectively prevent odor developing on storage. This microencapsulation is a patented technology, and the microcapsules basically size from 5 to 20 microns and are delivered in a water-dilutable slurry. The outer shell of the capsule is made of a thermosetting polymer which is heat stable up to 275 degrees, and the core contains the actives. These capsules are very ductile when in wet condition and do not break. It only breaks when it becomes dry, so they become ductile to release the actives. The actives are a mixture of environmentally safe biocides to effectively prevent odor development on storage. So it delivers deposits on surface which provide slow effusion of active biocides which are dermatologically safe, which means they're safe for the skin. Here we have a basic structure of the microencapsulated biocides. You can see the outer shell is made of a thermosetting polymer, which can be also used as a biopolymer for biodegradable applications. And it encapsulates the ingredients which can be biocides, essential oils, and other, which we'll talk about in the last slide. On the left, you have a microscopic image of Encap slurry. You can see the different sizes of the encapsules.
You can wind up, like quickly wind up.
Sure. We're just turning towards the end of the slide. And you can see how the capsules are depositing on the paper surface. So these antibacterial finishes have been tested according to the US and Indian standards, and we've used Staphylococcus aureus, which is a gram-positive bacteria, and K. pneumonia, which is a gram-negative bacteria. Specific testing also has been done according to the US standards for fungus, in which we use Candida albicans and Aspergillus niger. In that, we've seen that carbamate chemistry has broad antifungal properties, and combined with aromatic oils, it serves as the best suitable option for eliminating odor in craft paper. Here are a few of the tests to check the visual methods of checking efficacy of antimicrobial growth on craft paper. We basically use a Bacta slide, and on one craft paper, we use a layer of sterilized water, and on the other, we use a layer of microencapsulated biocides. So you can see that in control, after 24 ours, you can see visible colonies of the bacteria, whereas wherein we had a layer of microencapsulated biocides, no growth can be seen. In a similar way, fungus easily takes somewhere around 72 hours to be seen by a naked eye, and you can see that in the control where we did not apply any kind of biocide, there is fungal growth, and on the right side where the experiment had microencapsulated biocides, no growth can be seen. Again, this is the US standard test which was there for antibacterial efficacy, and here it is for the antifungal finishes. So this is the last slide of our presentation, in where we'll talk about what are the typical ingredients of the encapsulated biocides. So we have heat-stable fragrances, we have long-lasting antibacterial finishes, long-lasting antifungal finishing, antiviral, delivered essential oils, flame retardants, and it can be easily customized according to the customer's requirement. So that was all about my presentation today, and I want to thank IPTA for giving us the opportunity to present our studies today, and to all the distinguished members present here today. Thank you.